Welcome to the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our 6th lecture covering material from Chapter 4. And that's a long chapter. Realize this is in no way equivalent to our actual lecture where we discuss and practice the material in much more detail. This lecture describes a common laboratory technique called titration, which is an application of solution stoichiometry. What makes this procedure unique is that the reactants are carefully combined such that you can stop the reaction at a point where there are only products present. This point is called the equivalence point. The image shows a typical titration setup. The glassware involved is an Erlenmeyer flask, a burette, a funnel, and a beaker. A ring stand with a burette clamp round out the apparatus. The text describes the process of titrating a strong acid with a strong base. These images illustrate how we can use an indicator that turns pink when the pH is basic. The flask originally contains acid, and the indicator, which is colorless and acidic pH. Since the solution turns pink in base, we can utilize the visual color change to stop adding the base exactly when all of the acid has been consumed. Also notice the chemical reaction is written near the top of the slide. This is essential when doing titrations calculations. There is a virtual titration segment on MindTap, and we have a video describing how to navigate this assignment. Check it out for additional practice after this lecture. Standardization is a term used for finding an exact concentration, usually molarity, and by exact I mean 3 or more sig figs, which is really quite good. I'm going to start with a chemical equation, and KHP is not potassium hydrogen phosphide, but a rather large molecule that's very cumbersome to write. Since I know that it's monoprotic or just has one donatable hydrogen, I can just abbreviate the acid as HA. H is that donatable proton or the hydrogen. The problem asks for molarity. This is moles per liter of sodium hydroxide, and notice that we measured the volume, so we only need to calculate the number of moles of sodium hydroxide. Using reaction stoichiometry, we can start with the mass of the acid and calculate the moles of base. Dividing this by the volume in liters will give us our molarity. The molar mass can be calculated using titration. Again, I'm going to use HA to represent the acid since I know it's a monoprotic acid. This time, I have information on the sodium hydroxide, so I will use the known molarity to find the moles of base used, then use the reaction stoichiometry to get the moles of acid. The molar mass is grams per mole, so I divide the mass of the acid by the moles to get the molar mass. This question involves a diprotic acid. This means the acid can donate 2 hydrogens. Therefore, more sodium hydroxide will be required to neutralize this acid. If you've been using M1V1 equals M2V2 for titration calculations, it won't work anymore. So you're going to need to learn how to use stoichiometry to solve titration problems. The balanced equation is given. If the acid were an unknown, I would represent it as H2A. Use the molarity of the base to get the moles, and then the balanced equation to get the moles of acid. This result, divided by the volume in liters, is the molarity. We're going to wrap up this mini lecture with some homework. This problem is looking for molarity. Start with a balanced chemical equation and see if you can get 0.30 molar for a result. Thanks for watching. Please give this video a thumbs up and subscribe if you would like to see more mini lectures on the Professor's DuBois channel.